Okay, I'd like to dive a little deeper into the last example. So I just recopied it here. So if you have it in your notes, you don't need to recopy it. But it was this was the original system that we had called the coefficient matrix A, right? That's the coefficient matrix A, augmented vector B. It's really the system AX equals B. You can kind of, sometimes people like to call the reduced echelon form R for reduced or something, or row reduced or something. And then, so that's what I mean by this matrix here, calling R, and then this augmented column right here is changed, so I just call it B prime, just because it's related to B. And this had this general solution here, right? We saw last time. And what I want to do, so here's some things I'd like to say. So this, I'm going to call this vector P. And then I want to call these H's with subscripts. I at first had H1, H2, H3, H4, but then that annoyed me because it didn't match the variable, like, right here, right here. So that's X2. So I'm going to call that H2 and so on. So let's call this vector H4, this vector H5, and this vector H6. So the general solution, so the general solution to this AX equals B is X equals this vector P plus X2 H2 plus X4 H4 plus X5 H5. And of course, I'm running out of room. Let me try to write this better. Okay. So I'm just recopying this, just kind of put it in this really fully vector-y form, right? So that's the solution. And last time we noticed that P was a specific solution, right? Like P is a specific solution to the system because we can always set the free variables equal to 0. So we've checked that P is a solution. Namely that really we just checked that A times P equals B, right? But what about H2, H4, H5, H6? I said these vectors are also important. What about H2, for example? Is that a solution to AX equals B? One way we can try is we can actually try computing A times H2, or really that's just a matter of plugging in to the system, right? So check by computing A times H2. And let's just take like the third equation again here, like this one, and just plug in. You could actually do it. I mean, I would say pause the video and actually multiply this matrix A times this vector H2 and see what you get. It's a good practice. So I would pause it right now and do that. But we could also just check if we just take like the third equation, 3x 1 minus 6x2 plus x3 plus 4x4, let's forget this, minus 2x 6, right? If we plug it into the left, does this equal 5 when we, 5 being the number that's right here, right? Because this is the equation. Does it actually give us 5 when we plug in H2? And so H2 just has a 2 here, a 1 here, zeros here. And so if we try that, what do we get? We get, oh my God, okay. we get 3 times 2 minus 6 times 1 plus 0 plus 0 plus 0. And that is 6 minus 6, that's 0. Not 5. Not 5 factorial either, it's just 0. So yeah, we just get 0. Interesting. And you can check that AH2 is actually, if you multiply A times H2, you should actually get the 0 vector. And similarly, if you do AH4, AH5, and AH6, and you should pause and check these, you get the 0 vector. Okay, and so that's interesting. That means H1, H2, H4, H5, H6. So in other words, H2, H4, H5, H6, these all solve AX equals 0, not AX equals B. And so there's a name for this, the system AX equals 0. It's called a homogeneous system, right? This is called a homogeneous system when you have a 0 after the equal sign. That was the word system written very poorly. And so these are called homogeneous solutions. This is sort of something to do with A. It's sort of like saying, well, forget about B for a second, right? Like forget about the vector B. If we just think about this matrix A and forget about the vector B, then homogeneous solutions are considered the solutions to AX equals 0. Now, this is not so surprising. Like you might ask, why did that happen? Well, if you think about AX equals 0 for a second, that is the system with the augmented matrix A augmented by 0. And if you row reduce that, if you just think about what happens up here, if these were all 0 and I row reduced, I'm just going to get all these are still going to be 0. You basically can't affect. It's like this column didn't get affected by any row operations, right? Because it was all zeros. And so in fact, this would be a 0. So this actually reduces, this row reduces to the same reduced echelon form, except you have a 0 there. And then if you trace that back up to here, up to like sort of getting the solutions, you know, you have this 1 and 2 here, which those were the constants that showed up here, but they didn't show up here. This had to do with, right, those showed up, they had nothing to do with the constants that were right here. So if you put all zeros here and wrote it out, maybe I'll even do that, just like say for the second equation there. So I'll just say e.g. we have that x2 plus, I already forgot. No, x3 plus x4 plus x6 equals 0. And so there's no constant anymore. X3 is just minus x4 minus x6. And so you get the same set of solutions, actually. The solutions to x equals 0 are precisely, sorry for going back and forth so much, but they're precisely this right here. So the solutions to ax equals 0 are actually, it would be the exact same procedure, you just wouldn't have this vector here, right? You should check this out explicitly if you need to, like I sort of started to do here. You could rewrite, you could do everything we did in the last video and just see that you actually get exactly the rest. So in fact, this leads to the homogeneous solution, the general homogeneous solution is actually x equals x2 h2 plus x4 h4 plus x5 h5 plus x6 h6. And so what I'm trying to say is that there's a relationship between the homogeneous solutions and the solutions to ax equals b, right? So solutions to ax equals b that was x equals this vector p plus the sort of homogeneous solutions. Well, maybe I'll even just, maybe I should write it out a little better. So I'll just actually write this again, plus I feel like I'm copying this. I'm regretting making so many free variables. Right, whereas the solution to ax equals 0, oh, maybe I can be clever and use notability and just copy this and paste it there. Okay, so the solution is there, in fact. And so the only difference is the presence of P, right? The only difference is that this is, yeah, this is the only difference. Is the particular solution, I'm using P for particular, is the particular solution. P for ax equals b. And that's sort of interesting because it sort of says like no matter what the b is, and the b vector is, no matter what, going all the way back up here, no matter what these numbers are, I'm always going to get the same kind of solution. I'm always going to get this stuff in the solution, and it's just going to change what the particular solution is. So, so maybe I should write that down. In other words, regardless of the specific B, well, I suppose a B could make the system not consistent, so I should be a little careful. And AX equals B, let's just say as long as consistent. Regardless of that specific B, the solutions looked very similar. The solutions sort of contain the homogeneous solutions as part of them. Solutions are of the form, maybe I'll just say this, are of the form P plus the homogeneous solutions. Where P is a particular solution. It's a specific solution. And that leads to this, this kind of like the sort of mantra for this stuff, which is that the general solution to AX equals B is the particular solution plus the homogeneous solutions. And so that's kind of this like mantra that we get here. So all the general, if you want to take all the solutions to a specific AX equals B, because it just basically comes down to the fact that every time you row reduce A, you're going to get the same thing no matter what B is. And so the homogeneous solutions always sort of live inside that. And that's the mantra we end up saying. In the next video, I'll actually sort of give a more formal proof of this. It's nice to see some proofy stuff, but for now, I just wanted to say it this way. So I will stop recording there.